Hello students. So this is lecture number 14. In this lecture of particle physics, I'll be talking about the relativistic transformations. So let us start with the lecture. Again, I'm taking the notes from Perkins, and the notes we have already been provided with. You can see that relativistic transformation by meaning in most of the processes to be considered in high energy physics, the individual particles have relativistic or nearly relativistic velocities. That means they will be traveling very close to the velocity of light. This means that the result of the measurement, example lifetime or decay width or anything for that matter, of an unstable particle will depend upon definitely the frame of reference in which it is made. But what is our requirement is we can make the equations for them to be in such a way that they should obey a fundamental symmetry. What do we mean by fundamental symmetry? It means that the equations should be invariant under a relativistic transformation. That means once we are going from one frame of reference to the another, they should have the invariancy in their equations. So that the equations will have the same form in all the reference frames. Okay. So this can be achieved by formulating the equations in the form of four vectors. So these four vectors are very important, and we are going to focus on this part only when we are talking about the transformations. Okay. So you can see here that I told you about this, that this is the relativistic relation of a particle which is having a total energy E square is equal to P square C square plus M square C square. So this is the momentum carried by the particle, and this is the rest mass of the particle, right? Here, the momentum here is a three vector momentum. You can say that it is having the component px, py, and pz. Okay? And this energy is the fourth component of the momentum vector. Okay? So once we are going to combine energy with momentum, then the momentum can be called as four vector momentum. We're just going to see it. Okay? So in the units of C, when you are putting C is equal to 1, the equation will take the form E square is equal to P square plus M square. Whereas the components Px, Py, Pz and E can be written as a single component, okay, of an energy momentum 4 vector. So that means we are taking all these four parts, or you can say four vectors. Energy is a scalar, but we are just taking four vectors, so that this is the fourth component of that vector, which is behaving like a scalar quantity. So these four components will be a part of a single vector, that is P mu, and we can call this P mu as 4 vector, so that when mu is equal to 1, 2, 3, 4, one of the component is associated with energy and rest of the three will be associated with Px, Py, Pz. Now it depends upon you whether you are associating one with energy or four with energy. Okay, so here you can see that they are associating the fourth component of the four vector with the energy part. Okay, now there are various notations or conventions. So there is one another convention which is Minkowski convention, and here the three momentum components are taken to be real and energy is taken to be imaginary. That means this is a particular representation in which energy is taken to be an imaginary part. Okay, so that means there can be different conventions in which you can define them in a different way, but the equations of the motion which you are going to write will not change in any frame of reference. They are going to give you a similar result once you are talking about a particular parameter associated with that frame of reference. Okay, so here you can see that once we are going to square it, that means p square. This is nothing but 4 vector square. P square is equal to p mu square, where we are summing it to mu. So that means p mu square will be p1 square plus p2 square plus p3 square plus p4 square. And since in the Minkowski convention we have defined p1, p2, p3, p4 like this, you can simply put them together and you will get something like p square, which is the 3 vector. Okay, we are talking about 1, 2, and 3. It is a 3 vector part. And P4, which is the energy part, once you are going to square it, I square will be minus 1. And therefore, E square minus E square is going to come out of this. And from this equation, you can see that E square minus E square will be minus M square. Is that okay? Real and the energy component that is taken to be imaginary. So we are talking about the 4 dimensions where 3 are related to the space and 1 is related to the time. Now here you can see that whenever we are squaring it, p square, it is nothing but square over all the indices. Okay, so here we are having 4 indices, that is 1, 2, 3, and 4. So you can see p1 square plus p2 square plus p3 square plus p4 square. Now here this p which I am writing square, it is acting like a 3 vector and it is only talking about the space component, whereby the fourth term, which is the energy term, that is the related to time component. Okay, so 3 space and 1 time. So we are taking care of all the 4 vectors. Okay, so here p square minus e square is equal to m square. That can be seen from this equation which we have just solved it by putting c is equal to 1. This is a relativistic equation. So from here p square minus e square is minus m square. That means p square is something, this p square is something which has to be relativistically invariant when we are going from one frame of reference to the another frame of reference. That means the value has to be minus m square, where m is the rest mass. So what we have to do is, if P refers to the value of major frame in lab frame sigma, then those in the another frame, say sigma prime, moving along some axis, maybe x-axis, with velocity beta c, are found from the Lorentz transformation. That means whenever we are going from one frame of reference to the another frame of reference, we have to define the parameters or the equations of motion in such a way that the parameters of that uh, entity do not change, or that particle do not change. So here what we have to do is we have to use the transformation in such a way. So here you can see that transformation is given in this way. P mu prime is equal to alpha mu nu p nu. That means this p is the momentum in the, I mean, we are talking about the 4 momentums, right? So this P nu is a 4 momentum in sigma Lafreniere, and this mu P mu prime is the 4 momentum in the sigma prime Lafreniere. Now we are just trying to do the transformation as if we know P nu, how to find out P mu prime by doing the transformations. So the transformation is defined like this, and we are using this transformation, and here alpha mu nu is something like this. Now I have already told you in one lecture when we were talking about the particle wave equation that this gamma and betas are nothing but the matrices. They are the 4 cross 4 matrices. So now this alpha mu nu, which is a transformation constant, or you can say, okay, so here you can see that gamma is defined in terms of beta like this. Gamma is 1 upon under root 1 minus beta square. Okay. Now we want to know how each parameter or each momentum is associated with the momentum in the lab frame sigma. So each momentum in lab frame sigma prime is associated with the momentum in lab frame sigma in this particular way by multiplying with this particular matrix. Okay. So if you are opening this term, you are going to get all the terms separately. Okay. So P1 prime is this, P2 prime is this. Simply put this part here and open it. So this is a column matrix. This P nu is again a column matrix, and this will be 4 cross 4 matrix. So when you are going to open it, you are going to get these 4 terms. Okay. Now in terms of energy and momentum, you can simply put P1 prime to be Px prime, similarly P1 to be Px, That means we are talking about px, py, pz in sigma frame of reference, and px prime, px, py prime, and pz prime in the sigma prime frame of reference. So in that way, they will be related to this here. Okay, where of course if you are going to see the new parameters here, again these parameters are going to follow the same rule. That means p prime square minus e prime square is equal to minus m square, which is what we wanted, right? We wanted the transformation to be such that the fundamental parameters or the fundamental equations do not change. They remains relativistically invariant. So here also the p prime square minus e prime square is coming out to be minus m square. So the above transformation apply equally to the space-time coordinates if we are making the replacement from P1, P2, P3 to X, Y, Z and P4 to the time. Okay. So now you can see here that the 4 momentum squared in equation 1.1 is an example of a Lorentz scalar. That means the invariant scalar product of the two vectors is something like this. Fine. Now here, the another example is phase of a plane wave. Whenever you are writing a wave equation, you know that you write normally e to the power I kx minus omega t. So kx minus omega t is a part which is associated with the phase of the wave. So here k is the propagation vector and omega is the angular frequency. So the same equation when you are using the natural units h cut and c is equal to 1, so that phase can be written in this way. That means k dot x can be written as p dot x minus omega t can be written as et. You very well know how to write it, right? This you might have done in your BSc, but even otherwise you can just try it out. Okay. So if I will tell you lambda is equal to h upon p, so lambda k is nothing but 2 pi by lambda. So you can simply define p in terms of k and you can define omega in terms of e or e in terms of omega. And if h cut and c is equal to 1, then it will become more simple, right? So the same thing can be written as p dot x minus e t. We don't have h cut and c here. Now this particular thing in terms of 4 momentum can be written like this. That means p mu x mu. Because if you are going to open it, you are going to get p1 x1, p1 x1 plus p2 x2 plus p3 x3 plus P4X4. Whereas P4X4 is going to give you something like this because we are using X4 to be equal to IT. Is that okay? Okay, fine. So the Minkowski notation used here for 4 vector defines the metric, namely the square of the 4 vector P, where P is equal to, this is a 4 vector, which is equal to 3 vector and IE. So that the metric which you are going to define is 3 vector or 3 vector momentum minus the energy square. Okay. Now here you can see that in analogy with the space-time components, the components px, y, z of 3 momentum are said to be space-like. Okay. And the energy component E is said to be time-like. That is very true. I just told you that even if we are calling the momentum to be 4 vector, there are 3 space-like component and 1 is time-like component. And the time-like component is associated with the energy and space-like component is associated with the momentum. Okay. So thus, if Q denotes 4 momentum transfer in a reaction, if we are talking about any reaction, and Q is defining the transfer of the momentum, that how much momentum has been transferred from one point to the another. So then in that particular case, if this Q square is greater than 0, then it will be like a space-like process. Okay. And if this Q square is less than 0, then it will be like a time-like process. Okay. So generally space-like processes are used in scattering processes, whereas time-like processes are used for the masses of the free particle. Right? So this is all about the 4 vector notations. Okay, different notations is used in the text on the field theory. That means there are many ways you can define the parameters. So to avoid the use of imaginary fourth component generally, that we don't want this to be imaginary, we introduce a negative sign. That means we can have a different kind of notation whereby this imaginary part can be removed by introducing a negative sign and via a metric tensor. This is G mu. This is again a tensor which is in the form of a matrix, and that can be introduced so that the imaginary component of energy can be removed. And how it is done? It is done in this way, that if we are having two vectors, we can define the product of the two vectors, two four vectors you can say. So the product of the two four vectors can be written in terms of a0, b0 minus a dot b. So this will take care of the three vector, and this is nothing but the time-like component. Okay, so where all the components will become real just because we have introduced G mu nu. So if you see the structure of G mu nu, let us see all the it is a kind of 4 cross 4 matrix. So all the components will be 0 except these following components. So whenever mu is not equal to 0, it is always equal to mu is not equal to nu, it will always be equal to 0. And that means the diagonal component will be like this. That means for 0, 0 it is plus 1, 1, 1, 2, 2, and 3, 3 is minus 1. That means it is a 4 cross 4 matrix whereby the diagonal component will be 1, minus 1, minus 1, minus 1. And all other components will be equal to 0. So just by introducing this kind of metric tensor, we will have a different notation where the imaginary part of the energy can be removed. Okay. So this metric result in Lorentz scalar with sign opposite to those which we have just used for Minkowski space. And so the space-like or time-like for momentum is q square less than 0 or q square greater than 0 respectively. Same things have changed in the different notation. Okay. So sometimes to avoid writing negative quantities, we redefine the parameters, and those redefinitions will again help us to form the equation in such a way that the final parameters will not change in any frame of reference. The quantities will always be same. Okay, that is it for this part.